My name is Michael, and today I'll be presenting fine-grained recognition as HSnet search for informative image parts. This is joint work at Oregon State University. Our problem statement is fine-grained recognition. Given an image of an object, we want to recognize its class. As opposed to kind of object recognition, the categories here are fine-grained and discriminated by subtle differences. So here are some examples of what I mean. Different classes have similar appearances. So for here, we see a slaty back gull and a western gull. They're both gulls, but they look very similar. Well, one of the beaks is actually thinner, and the other wingtip is a little bit wider. So we see that it's subtly differentiated by parts. But then we have the same classes also have different appearances. We see here, there's two slaty back gull. One of them looks dirtier than the other. Actually, this is just because one of them looks like this during the winter. So we have some variations in gender, in season, and location. We also have our usual challenges of variations in pose, viewpoint, background, and lighting. And so here we see these variations in poses. We also have background clutter as a challenge. The remaining image context outside of informative image parts may hurt some recognition potentially. We see that the ovenbird, the background has a lot of clutter in it and could confuse recognition. We also see it against a sidewalk. And does having a bird against a sidewalk make it less of an ovenbird than one in the woods, for example? So parts may be most informative here. There's a lot of prior work on fine-grained recognition. I'll just highlight a few things briefly. It can be divided into part-based models. And the point of part-based models is to localize the parts and compare the corresponding locations and reason with the parts. And this factors out the variations due to the pose, the viewpoint, and the location. And that's what makes this potentially have higher accuracy, because it factors out the variations and takes advantage of the part annotations. Conversely, it's usually slower because the models are complex and part annotations are required for this. One can also just use general image classification. So just feed it into a CNN, which is what modern approaches use. The advantage is that this is fast, and it does not require part annotations. But because it's not using the part annotations, it potentially has lower accuracy. Our key ideas are as follows. We take a part-based approach. Unlike object recognition, we do believe that fine-grained recognition can benefit from removing background context and focusing on parts. We also take an iterative approach. So instead of just reasoning in one shot, we'll actually iteratively search for discriminated parts in the image using bounding boxes. And finally, we'll use a supervised and weakly unsupervised approach where we can search for parts even without part annotations. So our approach is an iterative approach, and at each iteration, we predict part locations, and we also predict the class. And at each iteration, we try to improve this localization and class prediction. Localization and classification is guided by something we call HSnet, which will be described in a few slides from now. The number of parts is fixed, and the final iteration will yield the best localization and class prediction. So we have a little animation here of our approach on a high level. HSnet first proposes some initial bounding boxes, and here for illustrative purposes, we show 4. And then HSnet evaluates the proposals, these bounding box proposals for classification, so it predicts fox sparrow. So we see here that we're only using information inside the bounding boxes. We're not using the features from outside the bounding boxes, just the features inside these boxes. Now, given this evaluation, HSnet updates the proposals and proposes new candidate bounding boxes. And then this, again, is fed into HSnet to make another prediction. And then after like tau iterations, tau you can select as a hyperparameter, you get your final prediction, and here it says ovenbird. So that's our iterative approach. And you can actually see this as a search-based approach. It's essentially just beam search, where the beam size is the number of bounding boxes, and your state is the history of locations and the sizes of the bounding boxes proposals. And you also have a heuristic function that evaluates the proposals, and you have a successor function that generates bounding box proposals. And that's why we call it HSnet, because it's heuristic and successor. And so now we'll dive into what HSnet is. Here, HSnet, this is our architecture. Once you look into it, it contains a heuristic H that evaluates the current state. So given the image and then like the convolutional features from the image, just from a CNN, And then we can take the bounding boxes and the features from it and then feed it into the heuristic function. And then LSTM will update its search history given the heuristic features. And because LSTM has memory, it can keep track of the search history. The features from LSTM are fed into a classifier, C, that makes the prediction at each iteration. And we have a successor, 8S, that proposes candidate bounding boxes based on the history of what the LSTM has. And then these candidate bounding boxes are parameterized by offsets. So the next bounding boxes are just added to the offsets. Heuristic is essentially just a region of interest pooling for each bounding box. So it converts it into a fixed size feature vector, which all of it is concatenated and then fed into a multi-layer perceptron. And this is fed into LSTM. Our successor function is a multi-layer perceptron that accepts the features from LSTM as well as the bounding box locations. And this is to predict the regression for the offsets. Here we describe our loss function. We have a supervised loss function, and we also have a weakly supervised loss function. In the supervised case, when part annotations are available, we have two parts of our loss function. We have a classification loss. This is a usual cross-entropy loss. We only evaluate this loss on the prediction on the final prediction of all the iterations. So here, it's the final prediction. And then we also have a parts location loss, which evaluates on each iteration. The intuition is, of course, we want the ground truth bounding boxes to be as close to the predicted bounding boxes. And then towards the beginning of the iterations, it's OK to have it further away. But then as you get closer to your time-bound tau, then you want to get as close as possible, which is the regularization parameter lambda. We also have a weakly supervised loss. So this is when part annotations are not available. We still have a classification loss. But now that we don't have part annotations, we have to use some other kind of signal. And so here we actually choose diversity as our regularization. And this is realized through determinantal point process. So we have a probability of having diverse bounding box candidates at time t. And this is using determinantal point process, where essentially you have a matrix of affinities between all the possible bounding boxes, omega, which can be pre-computed before all this happens. And then at each time step, you can just take the restriction of it. So then you can only look at the bounding boxes and then take the determinants of those, and you get the probability. We use Caltech-UCSD Birds dataset and Stanford CARS dataset. For the UCSD Birds and Caltech Birds, part locations are provided, but the bounding box for each part is not provided. And there are 15 parts, and each of the parts corresponds to parts of the bird. And in Stanford CARS, no parts annotations are provided. So we evaluate on some baselines to kind of see what's going on with the architecture and learn more insights about it. Our first baseline is a CNN, it's just a fine-tuned CNN. Our second baseline is a CNN with the ground truth bounding boxes. So here, we don't look at the entire image. We only look at the ground truth bounding boxes fed into a CNN. So we're just looking at the features inside these boxes and nothing outside of it. And so these features are concatenated and then just fed into CNN. Now notice that the ground truth doesn't have the bounding box size, so we empirically just determine 64 by 64 would be a good size for this task. Next, instead of just looking at a CNN, which is kind of just like a single shot kind of thing, we want to look to see if sequential reasoning does help. So we look at HSnet, and with the input at each time step is just one ground truth bounding box. And finally, in our fourth baseline, we look at HSnet with one bounding box, and here it's not ground truth. So we are using the proposals from the HSnet. And so, like, given the initial bounding box, then HSnet will just kind of scan around the entire image with just one bounding box instead of k bounding boxes. So our results show that HSnet is competitive with the state of the art. We see some accuracies from prior work. And we also look at the baselines and see what's going on with the baselines. We do see that the sequential reasoning improves over the single shot. And actually, this is in 2 slides from now. And for cars, similarly, we do see that it is competitive with the state-of-the-art as well. Here, we cannot do baseline 2 and 3 because we don't have access to ground truth locations. So why is LSTM needed? Well, the baselines demonstrate that sequential reasoning does improve over one-shot reasoning. And why do we need a determinative point process? Well, we need some kind of regularization when no ground truth part locations are provided, and we just chose diversity as one. And it seems that diversity, it does encourage learning diverse proposals rather than just singling into one part and potentially just making it kind of pointless. Here we show some qualitative results. The top row is a success case, and the bottom row is kind of more of a failure case, where you can see that as time passes by, the bounding boxes eventually kind of converge more or less to the ground truth parts. For the Stanford cars, we don't have annotations of the parts, so then we just look at the average image of all the cars, and then we can cluster the parts and then see what the parts are. And then it turns out that it looks like the parts are more or less in a good location for the cars. And so the dot is like the mean, and then the circle is like the standard deviation. In summary, sequential search for informative image parts does improve recognition, and our DPP regularization works well when no part annotations are provided. And unlike most object recognition, fine-grained recognition does benefit from focusing on parts. And thank you for your attention. And right now, I open this up to questions.